So this is the agenda that I am going to follow during this presentation. I'm going to express the abstract, the introduction, some related work, formulation for the quadratic assignment problem, the metaheuristics, the greedy randomized adaptive search problem, graphs for quadratic assignment problem, and results, discussions, and at the end, the conclusions. Starting with the abstract, one of the classic combinatorial optimization problems belonging to the NP-hard class is the quadratic assignment problem. The interest in solving the problem lies on the high computational complexity, as well as its applications in logistics, electronic circuits, allocation of gates in airports, among others. In this work, the greedy randomized adaptive search procedure Metaheruristic was implemented in order to search its solution. The main contribution of this work is the adaptation of one neighborhood structure contained in K-exchange in the post-processing phase to perform for the 29 large-scale instances of dimensions range between 64 to 254 taken from the QAP lib. Some of the introduction of this work is within the combinatorial optimization problem, there is a class of problems of high computational complexity, known as NP-hard, for which there is no known efficient algorithm that can solve it in a polynomial time. Given the inefficiency of these exact methods to solve this class of problems, taking in account the aforementioned approximation methods called Metaheuristics are used. Metaheuristics are general-purpose algorithms that guide a heuristic in the search for a solution in a strategic region of the feasibility space. The search strategies most used in the Metaheuristics are by neighborhoods or by the population with an approach inspired by natural process. This work focuses on a method of searching for solutions to neighborhoods with some solutions. So this work specific focus also on the search for solution for the quadratic assignment problem through the well-known Metaheristic greedy randomized adaptive search procedure. The QAP consists of finding an optimal location between n facilities to n location, considering the distance between the location and the flow of material between the facilities, such the cost of transporting materials is minimized. QAP is classic in combinatorial optimization and is classified as NP-hard. GRASS is an interactive procedure where each step consists of construct phase and improvement phase. In the construction phase, the constructive heuristics procedure is applied, obtain a good initial solution. The solution is improved in the second phase by a local algorithm. There is some related work in this document. So QAP was proposed by Copan and Beckham. Later in 1976, Chani and Gonzalez proved that the QAP is an NP-hard. So far, optimal solutions have been found using exact methods for instances of size 30. The QAP is used in many applications such as computer keyboards, design, manufacturing, programming, airport terminals, designs, communications process. An exact branch and bound algorithm are used with some variants to solve the QAP and was proposed by Recariol. However, recent solutions with different metaheuristics techniques such as genetic algorithms simulating annealing graphs are implemented to solve these problems. As I said at the beginning of this presentation, the principal objective of this work is the adaptation of one of the neighborhood structures in the post-processing phase of graphs in order to compare the best known value versus the outcome of the best found value. Within the results that are intended to obtain, it will be possible to visualize and verify if the implemented procedure is considered a robust method-heuristic to solve this type of problem. In addition, the efficiency of graphs was analyzed by running two sets of parameters. The first with alpha equals 0.2 and beta equals to 0.2. And the second with alpha 0.5 and beta 0.1. The rest of the parameters were performed for 29 instances. The formulation for the quadratic assignment problem is the next one that you can see in this slide. The QAP consists of finding an optimal location that minimizes the cost of the transporting materials among n facilities in n location, considering the distance between location and the flow of the materials between facilities. The QAP can be formulated by the combinatorial optimization model, as you can see in this slide. Optimization problems are based on choosing the best configuration from a set of feasible solutions to achieve an objective, and are divided into two categories: problems with continuous and discrete variables. Combinatorial optimization problems belongs to the second category. As an example, the greedy randomized adaptive search procedure. So, what is a method-heuristic? There are several successful methods in solving combinatorial problems. One of them is the greedy randomized adaptive search problem, or better known as a GRASP method-heuristic. It's one of the most recent techniques. It was originally developed at the time of the study coverage problems of high combinatorial complexity. Each interaction in graphs generally consists of two steps: the construction phase and the local search procedure. In the first stage, an initial solution is built that is later improved in a post-processing to perfect the solution obtained in the first stage until obtain a local optimum. The greedy randomized adaptive search problem GRASP is an interactive process. Each iteration consists of two phases, as I said: the construction phase and the local search procedure. In the first, an initial feasible solution is constructed. In the second, that we call post-processing, it is implemented through a local search applied to an initial permutation obtained from the construction. Later, it is improved by means of a change procedure until obtain a local optimum. Once the two phases have been executed, the solution obtained is stored and another iteration is carried out, each time saving the best solution that has been found so far. This is the algorithm. This is the cell code of GRASP. This is the GRASP for the quadratic assignment problem. So it should be noted that the solutions are permutations of length n. So you can see in the chart. Summarizing the procedure as follows: initial solution, construction phase, as I said, stage 1, generation of a list of a candidate which has previously been restricted by two parameters, alpha and beta. Then one is randomly taken of these candidates from which the first two assignments are derived. Stage 2, the remaining N2 assignments are added in relation of the greedy procedures. Once the process is finished, the permutation is completed, producing a feasible solution. Phase 2 of improvement, the solution generates from phase 1 is taken as the initial solution of some local search procedures. At the end of the procedure, a local optimal solution will be obtained, which could also be globally optimal. So this is an example. The neighborhood structures we use is to exchange consists of initial solution, generating a neighborhood with cardinality. This is an example on this table. Some of the results that we use in this search are explained in this chart. So as you see, there are 29 instances of dimension between or around 60 to 256. So the first column shows the test instances. The second, the heading of BKV, contains the best values known. The next column, 3 and 4, correspond to graphs with the parameters alpha equals 0.2 and beta equals 0.2. And the fifth column represents the computing time. Finally, the columns 6 and 7 are graphs with the parameters alpha 0.5 and beta 0.1. Their computational time is shown in the last column. So what are the things that we found with this result? Well, we can see in that result with table 1 in the gap 1 column that for the sets executed with the parameters of alpha 0.2 and beta 0.2, the percentage of error with respect to the best known value and the best known found value of the 9 instances was 0%. 12 of the instances ranging from 0.040% to 0.97%, with the error being less than 1%. With the respect of the parameters of alpha 0.5 and beta 0.1 in the column gap 2, it was found that again 9 instances share the error percentage 0%. Likewise, 12 instances have an error of less than 1. There was an increase from 2 of the 3 instances with a value of 1%, decreasing to 2 instances with error percentages of 3%. The instances that remain with the same error percentage of 19 to 21 were LIPA 60B, 80B, and 90B. For the 29 instances, it is observed that 72% of the test sets have a gap of 0. Everything was processed in a computer Intel Evo Core i5 with an average computing time of 189 milliseconds, and the difference in the maximum time in relation to the minimum in milliseconds was less than 30%. For the parameters of alpha 0.2 and beta 0.2. Finally, for the parameters of 0.5 and beta 0.1, the computing time it was a difference of 20%. So the results that we obtained in this in the search was really good. So in a conclusion, the principal objective of this work is the adaptation of one of the neighborhood structure in the post-processing phase of grasp in order to compare the best known value versus the outcome of the best found value. The search is carried out through two exchange neighborhood structure. The tests were performed for a wide range of large-scale instances taken from the QAP lib, with two disjoint parameter sets to constrain the restricted component of graphs in order to show the variance in efficiency of this approach. For the 29 instances, it is observed that 72% of the tests have a gap of 0 to 1. The remaining 28% include the rest of the instances. Therefore, according to the data obtained, it is shown that the implementation of graphs is efficient as well as robust.